introduction?
Wei Han.
Wei Han. Yeah.
Yeah.
So next presentation is former Apple AM series CPU design lead explains design trade-offs in Ascalon RISC-V CPU, such as ARM versus RISC-V, vector versus tensor, hardware versus software. Speaker is Mr. Wei-Han Lien. He is the lead CPU architect, Tenstorrent, Canada. 次のご講演は、元 Apple A シリーズ、M シリーズ CPU の設計リーダーが、テンストレント社、アスカロン RISC-V CPU の設計、トレードオフについて説明するです。例えば、ARM 対 RISC-V、ベクトル対テンソル、ハードウェア対ソフトウェアについてです。講演者は、ウェイ・ハン・リエン様。彼はカナダテンストレント社のリード CPU アーキテクチャです。So you start?
Yeah. Hi, everyone. My name is Wei-Han Lien. I'm Chief CPU Architect and also Senior Fellow in Architecture in Tenstorrent. So I lead the RISC-V, high-performance RISC-V CPU architecture design. I also lead a team working on the chiplet ecosystem. Right? So Tenstorrent is also building a chiplet. We're building AI chiplet, we're building CPU chiplet, we're building memory chiplet, we're building I/O chiplet. So I lead a team defining all the required elements for the chiplet ecosystem. The topic I'm going to talk about today is actually kind of deviate from the description, right? Because for that, I see there's more about CPU design, not about why RISC-V, right? So last year I traveled to like 20 countries, more than 20 countries. I talked to government, I talked to big enterprise, right? Talk about all the chip design we actually making AI RISC-V. Right? I see something actually happen in this world. Semiconductors suddenly become such critical component, not only for a big enterprise, but for a country. Right? Why is that? Right? So you look on what pandemic actually demonstrates that semiconductor, right? This industry is critical for any company or any country, right? Economy, because the leverage, right? The price leverage of the semiconductor. So if you have a car, $440,000 to sell it, you're missing on one chip, $10, right? You cannot actually make that car. So the leverage of the semiconductor is so big, so important for the economy. After the pandemic, the global supply chain system people believing in the last 10, 20, 30 years is completely broken now. Because every government, every enterprise is starting to understand that when there's a supply chain issue, right? When there's an export control on your product, your country or your company going to be devastated, right? So that's why they look on semiconductor as a strategical. I see the presentation, right? There's a lot of strategical investment because it's a national security issue, right? So it's critically important for the quick semiconductor. Then people say, okay, let's develop in semiconductor. And what they are looking at, the first two components they are looking at, right? Of course, it's a CPU. Because CPU is like today, your water, right? And electricity. Imagine there's no CPU in the world. The whole Tokyo economy is going to cut to half. Like server doesn't work, car doesn't work, critically important. So that's why people start looking at, so okay, what kind of design I can invest in CPU? The second, of course, is AI, which I'm going to talk about as well, right? So Tenstorrent as a company is even a startup for 400 people. Now, we're actually developing two critical technology, right? One is the CPU, one is AI. And AI definitely going to change in the world, right? Like the OpenAI just demonstrate, it's just started, right? So for that technology, everybody or every country in the world treating as existential threat, right? If you don't have AI, my industry might not be able to continue, right? Because AI can come in there, turning things upside down, and it's a critical element to do, right? So it's very important. So that's what these two technology, like I see the presentation from Maddie, right? Two critical technology components. What is that? CPU and AI. Right? So today, I'm going to talk about RISC-V for digital transformation because the current era you are in today, right? 100 years from now, you look back, people will treat this as a critical history juncture, the second industrial revolution, where the machine intelligence replaced the human intellect. It's just how significant this time is. And that's why there are two element components in the AI. One is the algorithm development. The other is the computation required to compute that algorithm, right? So Tenstorrent is working on the computation part, right? So that's why I want to demonstrate to you like why this is so important, why the RISC-V playing such important role in the digital transformation we are experiencing today. The new industrial revolution is coming. So the next 10, 20 years will be a historical juncture for the human being, right? So you are actually personally see this happen. Like I already mentioned, the digital transformation we talk about is about AI, right? So AI go into any industry, they change the car industry, and then eventually they will change in the movie industry, they will change in even the chip design industry. Tenstorrent is working on how to using the AI design the chip. NVIDIA is doing that. So all the future, every industry AI going into is gonna be turning upside down, right? So everybody had to prepare for that. That's the threat, right? But there's also many good things can happen for the AI. Like medical, for example, personal medicine will be available because of AI. Your kids' personal education will be much, much cheaper, much better quality because of AI. So this is what we call the digital transformation. But what's the behind of this digital transformation? What does it mean, right, in terms of computation? So how we actually landing here, right? So if you look on history, right, it's all coming from the transistor technology. Right, 1947, transistor invented. Then transistor, this technology, semiconductor actually enable two things to happen, right? One is the upper one, we call compute. The other lower one is called connectivity, right? So on the upper side, there's a transition, right? So like everybody is familiar about mainframe computer before 1996, right? Suddenly digital sell to, I think HP. I think HP at that year is kind of marking the end of mainframe computer and the rise of the personal computer, right? In 2007, PSMI get acquired by Apple. I start working on the iPhone chip. That's where the first personal computing device you can carry every day, everywhere, go to any places, right? That's what we define as the first real personal, mobile personal device, right? And what's happening is that you, as a person, you start generating tons of data, right? And then this tons of data is actually propelled by the connectivity, which is shown below. 1993, there's a Netscape invented, you have the internet. And then 2000, you have 3G wireless. That's where the personal connectedness, actually connection is happen. Then this personal connection combined with the personal compute you have, and that start propel the AI forward because people start generate tons of data, and then they will transmit it from your personal device to the web, right? To the data center, you start seeing a lot of data, and then suddenly people realize their data has the mind to go. That's where the data mining, this turn start happening, right? Use a lot. 2012, when the semiconductors start pushing forward, and then you start seeing there's AlexNet being developed, and that's where the golden era of the the AI models start happening, right? Starting on 2012. And then you can see this is coming from OpenAI, right? The model, so like I talked about, there's a two part of the AI computation. One is the algorithm, right? That representing the complexity of algorithm and also the efficiency and accuracy of the algorithm. The other is the amount of data generated every day. right? The model complexity starting from 2012, growing exponentially, right? The model size growing every 4 months, they double their parameter size. So ChatGPT 3 is 300 billion parameter, and ChatGPT 4 rumored to be 4 trillion parameter, right? So the amount of computation required for the model and for the accuracy for its capability is keep increasing. Coupled at the same time, the human being generate 2 to the 18 bytes of data every day, right? These two, when they combine together, compound together, is a huge computation problem. Nobody actually know how to solve today. That's why there are so many people, coming up, try to invent in the semiconductor technology to solving this computation problem. You are not only not doable in a reasonable amount of time, you have to do it in a reasonable amount of power. Very complicated, right? That's why NVIDIA now is $1 trillion company. I see there's a huge amount of demand of this kind of thing still remain to come. And that's why we are sitting here today, right? Talk about this. And then from our perspective, right, solving this massive computation problem cannot be solved sending all the data to the data center, right? The strategy you have is actually you have to solve this computation everywhere. Like you have to solve the computation at the edge, right? You have to solve the computation at the client side. And then eventually there's a post-processing going to the data center, do the true inference or training. Like I continue to talk about, right? So if you look on the human body, how they actually interact with the external interaction, you touch your skin processes as a itchy, as a funny, as a pain, and you propagate to your brain, right? So there's a pre-processing already happen at your skin side, at your hand, before you send it to your brain. So if everything have to send to your brain, right, I think your nerve has to be probably a couple thousand times thicker than what you have today. This is similar to what the AI problem today. Huge amount of data being generated every day and huge amount of computation required. Not everything can be sent to data center. So Tenstorrent, right, understand this, and that's why we invented the architecture solving the AI computation problem in 2 parts, right? We want the scalability. We want to have consistent architecture and a uniform software flow for all the computation in there. Look at the car today, right? So you have the edge inferences like going on, and then when there's an exception happen, the car cannot process. They have to send to data center to training, right? So there's a pre-processing, understand the exception case, and then they send to the bigger model for the training. So that means they don't need to have inference model at the edge, and then they also have the data center training, right? So we want to make this process actually uniform, right? So our AI element is actually scalable, right? So that's mean you can take certain amount of compute and make it as an edge, but you also can go into scale to a much bigger computation like a training problem. So RISC-V, right, coming to serving this purpose, right? So I will talk about like how we actually utilize RISC-V as an embedded processor for our AI. I'm also talking about using our RISC-V processor for the general purpose compute, right? So that's why this is actually coming with a handy, because if you look on the software stack all the way from the edge, from all the way to the data center, this complexity, right? We can have slight deviation about the requirement of the different computation, like edge compute, maybe the power efficiency, and also something need to be accelerated, DSP, something, right? They all can be customized with RISC-V. So underneath, there's a unified software architecture, while there's a lot of variation you can introduce based on your application level on the different level of the services. Right? So that's why RISC-V is important, because open architecture, you don't have the license. Like I was coming from Apple, you have to talk to say, I license your architecture, what kind of product you have to build, everything, right? And then for the RISC-V, you can take the ISI, implement as many variation as you want for the product you are building without talking to any license fee. So that's why this is the beauty, right? Coming to just the right place at the right time. We're actually also using, like 2016, this company already using RISC-V, using as an embedded processor, right? And then sending the instruction to the accelerator. So it's actually, you see 2 very distinct different usage. One is mature ecosystem, right? Like a server system, the other is embedded system, like specialized embedded processor system, like we do in the accelerator. So Tenstorrent, right? 2018, like I mentioned, $300 million raise, 350 million employee, keep growing, right? So the team coming from AMD, Apple, like Tesla, NVIDIA, and we already have 3 machine learning chips, right? We have Grayskull, Warhol is already shipping now, Blackwell already tape out, right? Ascalon is a high performance RISC-V program leading designing. And you can see this is the car, this is the kind of the 32 chassis system we are building in the lab. The team, right? Of course, Jim Keller know his name in many different company, right? So Tesla, AMD, Zen, he invented the Zen, and then Apple M series Apple processor, right? And then also digital processor. Everything he touches is turning to golden, right? I'm just joking, say that every company Jim Keller joined, right, become a $1 trillion company, right? Apple, right, Tesla, and AMD is on its way, right? So if you follow Jim Keller buying the stock, it might be a good investment long term, right? So I'm just joking about it. We already have an AI product, like I mentioned, right? 2021, we have the Grayskull 22 Warhol, and then Blackwell just tape out is 6 nanometer technology. You can see that the transition is from PCIe product 2021 to more scalable product for the larger system, right? We're building a scale technology, and that means you can connect in multiple chip together and serving different purpose, training and then high-end inference, or smaller, just one single chip, right? And then the Blackwell is we start putting the heterogeneity, right? So the 2 important components, like I mentioned, in the computing in the future and in the AI is CPU and also the AI acceleration. We start integrating as a heterogeneity, and we start building next generation. I'm leading the team, right? Building the chiplet ecosystem. There's a Quasar, right? Which is our machine learning chiplet. I'm leading the team building what we call Aegis, right? Which is our CPU chiplet. When we start building chiplet scalable system together. And then this is kind of repeat my message, right? So the RISC-V actually in here is being using in 2 different domains. One is the 10.6 core, right? We are using the AI accelerator itself is using RISC-V instruction as its a fundamental programming paradigm, right? For doing the accelerator. So you can actually program with a RISC-V, driving the instruction to the accelerator and manage the traffic, manage the transfer, right? It's pretty capable of doing that. And then using the standard C programming underneath that. And then the other part is actually the Aegis processor, which is the traditional computation for high performance. So it has robust programmability, right? Because everybody know how to program C++, right? Python on the computer, like CPU. And what it actually is require a very mature software ecosystem for the adaptation, right? But for this side, the application RISC-V, because it's embedded, we build a whole software stack by ourselves. So the ecosystem compatibility outside is completely irrelevant, right? So we're building our ecosystem, like our compiler, machine learning compiler, everything, right, using the RISC-V. So this just demonstrates like 2 very different usage model of the RISC-V, right? One is a mature server, the other is actually accelerator, which has a very special, application, right? So the RISC-V is great for both of those. Talk about scalability. Like I say, we believe AI compute need to be everywhere. So the architecture itself is actually manifest that concept, right? So the accelerator and the machine learning scalable 10.6 element is that you can see our chip is actually stacking by this we call 10.6 cell, which is connected to the NOC, right? And depending on how large you want to be, how much compute you want to be, right? You can connect to different topology. In this case, we connected 2D torus NOC technology. And you can see internally, there's a 5 RISC-V processor, one processor responsible for, collecting the package, right? So someone send the package is kind of NOC manager, right? For this receiving, the other is actually for the sending, and 3 internal RISC-V processor is responsible for manage the traffic, manage the instruction going to the accelerator. Right, so you can see this simple component here is a repeatable element, and it's actually based on the RISC-V, right? So we building this. And then you can see this is our product, right? So the second generation wormhole, like I mentioned, we have scale technology going through the Ethernet, right? That Ethernet technology using this kind of proprietary RDMA technology, they can using Ethernet switchless connect together, right? So we don't have need external switch like NVLink. You can see this is like 32 of this car, 32 chip connect together. This we call Galaxy system, right? 30 petaflop, right? 32 node, and then 6 kilowatt power consumption, something like that. And this is the first generation, second generation technology. The black hole coming by with 6 nano technology. This will be even more powerful. So one thing I want to keep this going back with is that Tenstorrent AI is a scalable technology. That's why we have LG, we have Hyundai, we have Samsung, we have all this company coming to us, working with us, is because our IP is a licensable element, right? Depending on your need, where you need in the client device, in the consumer device, or car, something, depending on how many computation you need, you can instantiate this in the IP, or you can buy our chipset, right? For your car, for certain application, right? You can put it in together with the system chipset, and then we have the scale technology. You can scale out in the system level, right? So you can see the software we are building and the system we are architecting is actually coming from one tiny single 10x element all the way to the large scale system and consistent with the one software stack, right? That's the beauty. Yeah. And then this is just to tell you like our software system ecosystem, this is we call end-to-end flow. You basically writing a PyTorch, the compiler will compile that for you all the way from top to bottom, map to the system and run. Right. This is easy for the development because when you develop the new AI software, you want to see its functional immediately work, right? So you just take this and push the button, and you will map to our hardware and run it. Performance might not be great, right? This is for you to validate your system, and then we have another flow we call Metallion, right? So one flow is called PyBuddha, right? So you have the easiness of the use of the machine from the algorithm all the way to the hardware. But the other one is much harder. It's like a CUDA flow. You have the library to call, and you can actually program the RISC-V processor in there, right, with the C, and tell them what exactly you need to do. And we're building a lot of actually library around it, like FFT or something high performance computing library. You can use that, right, to call it and instantiate it. But you also leave you the control about what exactly you want the accelerator to do, right? So this gives you a way to control the hardware precisely, and this is great for the deployment of the machine. You have an algorithm, you know exactly what you want to deploy a massive amount. You can spend 3 engineers and then working on this flow and clearly mapping in an efficient way. So this is another flow. So we talk about scalable RISC-V AI technology. Then the next one will be scalable RISC-V CPU. So Ishi-san here and I were building this Ascalon, although the superscalar process is the AY decode machine is pretty powerful, right? We expect architecturally will match Zen5 performance in 2024, in 2025 next year. And then it has all this advanced feature, you can read about it, right? The beauty of this thing is that going to the scalability story, right? So our AI is scalable to the different device and application. We want the CPU to be scalable. So when we actually proceed the CPU, we're actually building in a way they can parameterize to support AY, 4Y, 6Y, 4Y, 3Y, and 2Y decode machine. They will be using on a different application because different application on the client device, they don't need a 6AY decode machine, right? Because of the power constraint. So we have 2Y for that solution. So the solution for the CPU is also scalable, right? So you have AI scalability, and then you have the CPU scalability. And when we design the CPU, we also perceive the CPU will be part of the AI computation because AI computation in the future is getting more conditional and getting more random. So we want to pair with the CPU actually has very flexible programming semantics and also can do a lot of things AI cannot do. AI is good at what? Accelerator is good at batchable design, right? Groupable computation. Random processing is not good for AI. But if there's an AI computation in the future, they have this problem, we can allocate to the CPU, which is what we call heterogeneous compute. We integrate them together in the future chiplet, right? So in this example, I just demonstrate, say that the green part is actually the CPU, the blue part is actually AI. You can map AI computation 1 to CPU, 2 to the AI processing. When we actually integrate the CPU, we also make a CPU and GPU has the same kind of abstraction level, right? So they actually look the same on the higher level from the software programming perspective in terms of its topology and message passing capability, right? So this, if you have these two things, then you can easily integrate the CPU into the computation of the AI compute. Ascalon can be integrated as a cluster, right? Many people use study CPU, right? So this is a core Ascalon, and it has two NOC, one is the XC, one is the Chai. The XC is actually using for message passing, Chai is using for cache coherent traffic, right? So you can integrate with the cache. So this is kind of our cluster architecture, and this is the die shot of our design, right? So design is well on the way. We plan to tape out the end of this year, right? You can see this is a core, right, CPU in there. And then, how much time we have? 6 minutes, okay. I just gonna go quick. Then this is our chiplet architecture. We are basically putting 32 core chiplet, and they can be connected together to forming this Aegis chiplet, right? So this is the kind of the flow plan and die shot. You can see there's a CPU here, there's a NOC, there's a die to die, right? So we're gonna tape out this end of the year, and then you can see this kind of blowout version of that, right? So like our company's strategy is also about scalability, right? So one key thing we are developing is actually scalable chiplet technology. You can see that we can take, this is kind of logical view, not the physical view, right? CPU chiplet with AI chiplet, memory chiplet, and PCIe chiplet compose a heterogeneous compute system for the future AI. And this is the product we actually aim to competing with NVIDIA on the 2025, right? They have Grace Hopper, and we have what we call Grendel heterogeneous compute. And then just talk about the composability of the chiplet system is that this is like, we can compose a Aegis only server, right? 128 core server with the DDR memory, with the PCIe. And then we can also put in as a high-end system. Like if I see the memory bandwidth is important for high performance computing, I can put in the HBM in there. So the memory subsystem in this design just become a lay binding decision on the package level for your product, right? You don't have to redesign the CPU because CPU already consider maximum bandwidth you need to do to design the maximum system you have. So now you have tons of flexibility to compose the system. I can put in DDR, I can put LPDDR, GDDR, or HBM, right? Depending on your memory system. That's the beauty of the chiplet system. And this is how the Aegis compose 128 core system, right? 4 of that stacking together. You can see that this is 32 core, 32 core, 32, 32 core, right? You compose a 128 core system through the die-to-die interface. And then on the side, there will be a memory controller chip that I didn't draw here, but this is just to give you an overview of what we are working on. This following just give you a couple examples, like the work we've been working on, right? So D2 can be using the wearable, right? Some people are actually interested in using that in the wearable, right? So our CPU can do that. And then we can do in the mobile computing as well, right? So we have DA and then with D4 combined together, we can serve in the mobile computing market, right? Cell phone market, I came from Apple. So this is kind of what they call big little strategy, right? And then we can go in automotive, right? They can license our IP, they can license our chiplet, right? It's auto-graded chiplet, and then we can actually sell to them. They can use, SLD, fully redundant system using the chiplet, right? That will work. And then we can also go into the DPU market, right? Because CPU can serve in the compute, and then we just need to connect the right packaging processing. We can do the DPU. We can also do the video server, put in the encode, encoder, right? With the CPU, we can serve in as a video AI-based, video server, right? So the message is that we are in the spatial time era in a human being, right? AI compute is necessary. And how are you going to address that? And then I think Tenstorrent has the right strategy, and RISC-V is really important for this strategy because it's open source. You can modify it, right? We're using your accelerator. We're using our general purpose CPU. And because it's open, you can build in any product based on this instruction set, right? So that's the beauty of this. And this architecture coming just at the right time, at the right place, right? Because we are actually working on this compute everywhere. If we had a restriction of the licensing, we won't have this leverage or the liberty to making so many different wide variety of products, which is the customer want us to build. So we engage with the auto market, high performance computing market, consumer market, right? So we are everywhere, and this strategy actually fit out very well, right? Because every country, every company, they need to have a semiconductor decision to address two critical computation demand, CPU and also AI, and we have that, and our strategy fit out very well. Thank you.
Thank you, Wei-san. Thank you very much. So the session is open for discussions. So any questions? ご質問あればぜひどうぞ。
You're welcome to talk to me when you after the. I will.
午後も